Hi everyone, I'm Adyasha Mohanty, a PhD student in the NAV lab advised by Dr. Grace Gao at Stanford. I'm excited to present our work titled Tightly Coupled Graph Neural Network and Kalman Filter for Smartphone Positioning. Learning-based approaches are becoming really promising for improving GNSS positioning. This is because of four reasons. First, learning-based approaches can provide better performance under uncertain measurement noise models. Secondly, they are adaptable to dynamic environments without requiring significant parameter tuning based on the specific environment. Third, given adequate amount of input and output data pairs, these models are able to better capture hidden and nonlinear relationships between the inputs and outputs. And lastly, there are certain learning-based approaches which can indeed generalize better to unseen environments if trained on the right and diverse number of datasets. Let us take a look at some prior learning-based approaches that have been proposed in the context of improving GNSS-based positioning. First, we have deep neural networks, which try to either learn a position correction or optimize for positioning performance using gradient-based or other methods of optimization. We also have works that try to capture the temporal relationships present in the GNSS measurements, specifically works that use LSTMs and recurrent neural network or RNNs, and they have been used for learning position corrections as well as for scenario recognition. We also have approaches that leverage convolution neural networks, which is super common in the computer vision community, but in this context, they have been used for non-line of sight and multipath detection and classification. And lastly, we have hybrid methods, which make use of the benefits of both learning as well as model-based approaches. And this is a relatively recent area of work, and there have been some methods that try to learn position corrections directly and improve GNSS positioning. We understand that hybrid methods are becoming more and more powerful. This is because learning-based methods are not able to fully utilize the known structure of satellite signal. On the other hand, model-based approaches can capture satellite geometry by using metrics such as top or even the line of sight vector. They can also give us the value of the expected measurements using metrics such as pseudo-range residual. We can also understand and infer the signal quality by using metrics such as the CN naught as well as pseudo-range uncertainty. In this work, we propose a hybrid approach that is inspired from our previous work that was proposed last year at ION. Our last year's work combined a graph neural network with a Kalman filter. In this work, our Kalman filter provided initialization and a coarse positioning, as well as input conditioning for features that were then fed to the GNN. The GNN then learned a position correction, which was applied to the coarse position, and we used the final predicted position, which was much better than using either model-based or learning-based approaches. In our work, we also had to adopt and design a custom graph neural network or GNN by using different satellite positions as nodes and preconditioned measurements as features. Here we illustrate a sample feature vector for a particular node. Even though our work showed really promising results on a diverse set of datasets, there were three key limitations. First, the GNN did not adapt to dynamic graphs. Secondly, the Kalman filter was manually tuned. And lastly, the GNN and Kalman filter were optimized separately. This indicated that there was an upper bound on how accurate the GNN could be because of how well we tuned the Kalman filter. Thus, in this work, we propose three contributions that directly address the limitations of our prior work. First, in order to make the GNN adapt to dynamic settings, we improve it by using extended features, novel edge creation techniques, as well as inductive learning. Secondly, instead of manually tuning the Kalman filter, we design a learnable Kalman filter by using a technique commonly used in machine learning known as backpropagation. And lastly, instead of optimizing the GNN and the filter separately, we deeply couple them using joint training and a unified optimization objective. The outline of my talk is as follows. First, I'll describe the proposed framework, the modifications made to the GNN. Next, I'll talk about the learned Kalman filter design, and then finally explain how we deeply couple both the GNN with the learned Kalman filter. The second half of the talk will focus on experimental validation on real-world datasets, and lastly, I'll conclude my talk. So first, let me explain the extended feature set of the GNN. So as a reminder, our prior work used the line of sight vector and the pseudo-range residual. Now these features were adequate to capture the most basic information about the satellite signal structure. However, we can construct more features to capture even more information about the signal structure. Namely, in this work, we extend the feature set to include the pseudo-range uncertainty, which gives us relative weights assigned to different measurements. And we also use the C and naught values, which indicate the likelihood of certain signals being exposed to multipath effects. Moving on, we also explore a novel edge creation techniques to establish edges in the graph. Although there are many choices of constructing these edges, we construct them using the cosine similarity metric, which helps capture correlations in processed features that are constructed from the GNSS measurements. Additionally, the similarity metric quantifies how closely two nodes, or in this case satellite positions, align in a high-dimensional space. If the similarity exceeds a certain threshold that is empirically determined, we establish an edge between the nodes. So here's an example of the GNN graph. We isolate two nodes and an edge between them, and then the similarity matrices for different time steps look like the following. So if we have a high similarity that exceeds the threshold, we connect both the nodes. And lastly, we also explain how we explore inductive graph learning in the GNN. The idea behind inductive learning is that even though we can train on only a fixed set of graphs, we should be able to generate representations on new graph nodes, especially at runtime. For this work, we adopt a framework proposed at Stanford known as GraphSage, where instead of directly learning the node embeddings, which is complex and high dimensional, we can instead try to learn a function that generates the embeddings for various nodes by using sampling and by aggregating features from a node's local neighborhood. And the benefit of this kind of framework is that it lets our graph, GNN, or graph neural network, adapt to various graph structures, which in turn helps capture a diverse set of errors in the urban environment. Moving on to the learned Kalman filter, let me first explain the key modifications that we have to make from a traditional Kalman filter. The first and most important modification is that we need to ensure that the filter that we have is differentiable so that we can leverage backpropagation techniques and ensure that the gradients flow smoothly. Secondly, instead of using fixed parameters, we also want to update the filter parameters in an adaptive manner so that we can adjust the Kalman filter to the associated measurement noise that we have given the measurements. And lastly, we need to modify the measurement update step that we have in a traditional Kalman filter so that it directly takes intermediate observations or positioning corrections from the GNN. So to summarize how this entire thing works, we start from raw measurements, which are the GNSS code carrier Doppler measurements, satellite position velocities, as well as a coarse receiver position from a baseline method such as weighted least squares. We use feature pre-processing and then move on to the learn Kalman filter component. We predict using traditional system dynamics, and then we obtain the propagated state and covariance. In the measurement update, we then take intermediate observations from the GNN and predict a 3D position that is used to compute the mean square error loss. We then backpropagate the loss with respect to the parameters of both the GNN and the Kalman filter so that we can update them jointly, and then use this predicted correction and the updated parameters at the next time step to further improve our positioning performance. So moving on, I'll next talk about the experimental validation on real-world datasets. We evaluate our approach on the Google Decimeter Challenge 2021 datasets that were collected in California. We use about 49 traces that were collected in cities such as Mountain View and San Francisco for training, and we test our approach on 13 testing traces that were collected in cities such as San Jose and Sunnyvale. Note that this split is done so that we can follow the traditional training testing split as well as make sure that we have enough datasets to benchmark our approach against prior proposed works. But additionally, we also test for generalization capabilities of our approach in new cities such as Los Angeles. As baselines, we use a Kalman filter that has no learned components, but we tune the parameters with Bayesian optimization to further stress test our approach. We also use our prior work from last year, which is the loosely coupled GNN and Kalman filter. And lastly, we use the attention-based position correction work, which was proposed at ION 2 years ago and uses a set transformer-based approach to learn position corrections. Here is an entire list of results, but due to interest of time, I'll only be talking about qualitative results in terms of the trajectory tracking with respect to ground truth and some statistics about the positioning error, especially the mean, median, maximum, and minimum errors. So here's an example trajectory that shows how our approach can closely follow the true trajectory that is collected in San Jose. So as you can see, we indeed are able to follow the true trajectory quite well at a lot of places. However, the prior work from last year is not able to do so. Furthermore, if I zoom into certain sections, you can see that this is indeed the case for different sections of the trajectory. Note that for easier illustration, I've only plotted the loose GNN and Kalman filter baseline in this map. And additionally, from last year's work, we showed that this baseline outperforms all the other baselines by a huge margin. Similarly, I show another results that was collected in Sunnyvale, and even in this case, the predictions from our approach indeed follow the true trajectory quite closely, while the loose chain and Kalman filter fails to do so. Again, by zooming into certain sections, we can see that even in straight segments and in segments where we have buildings on one side of the street, our approach can still closely match the true trajectory, outperforming the baseline and offering about 0.9 meters mean error in north and about 1.1 meter error in the east direction. Now here I would like to summarize the positioning errors on all the test datasets only in the east direction. As shown in the highlighted cells in the last column of this table, our approach can outperform all the baselines that were tested in this work with respect to every single metric and show significant positioning and performance improvement in the east direction compared to others. What is notable is that the minimum error is about 0.6 meters, which is observed on certain traces in Sunnyvale. Similarly, we show the positioning errors on test datasets that were collected in the north direction. And even in this case, as shown in the highlighted cells, our approach can outperform all the baselines with respect to every single metric. Even here, what is notable is that the minimum error that we can achieve in this direction is about 0.7 meters. So both in the north and in the east direction, the minimum error is sub-meter level, which means that our approach is indeed a promising way to think and formulate the whole problem of smartphone positioning and leverages hybrid method to increase the power of the positioning corrections that are applied to the initial position estimate. So to conclude our work, we designed a framework for improving GNSS smartphone positioning by deeply coupling a GNN and a learned Kalman filter. We increased the GNN's measurement modeling capabilities by looking at an extended feature set, exploring novel edge creation technique, as well as applying an inductive graph learning framework. We jointly updated parameters of the learned Kalman filter and the GNN weights by using backpropagation. And lastly, we evaluated our approach on real-world datasets that were collected in the urban environments and outperformed existing learning as well as model-based approaches. I would like to acknowledge Google for making the Smartphone Decimeter Challenge datasets publicly available. I would also like to thank NavLab members for their great feedback and insightful discussions. Thank you, and if you have any questions, please feel free to check out our paper on the ION GNSS Plus website. Thank you.